Thank you, Burcu Sakız, for sharing your valuable insights with us. And now we are continue with the post-quantum transition and what rise of quantum computing could mean for the future for blockchain technology. Please welcome Mehmet Emin Gönen from TÜBİTAK to the stage.
Hello everyone, my name is Mehmet. I work as a cryptography researcher and I am the member of TÜBİTAK BİLGEM, which is Turkish National Security and Research Center. And today I'm going to talk about the post-quantum transition, which is really hot and interesting topic. And actually I try to give less technical details, but I am a researcher. I have some professional deformation. Therefore, if I started to give more technical details, please warn me and somebody can give some signal to me. Then I will try to make it simple. Okay, actually the clock is already started and I hope at the end of this presentation you will understand why this is so important. Okay, let's start. First of all, we can say that, okay, in blockchain space, it seems there are a lot of complex cryptographic algorithms, but we can say that we have two main primitives. The first one is hash function, and the second one is digital signatures. And that hash function gives us a fingerprint for data, and digital signatures gives a proof of membership. Therefore, if you have private key, you can spend your money using that private key. And these are two basic structures. Okay, besides them, there are a lot of advanced topics also in blockchain space, pairings, aggregation, zero-knowledge stuff, SNARK protocol and Starks protocol. But let's first focus on that two main objects, and after that you will see that we have some problems regarding that architectures. Okay, if you look at that two objects, hash functions and digital signatures, they are really secure against classical computer, and there are no problems for them for classical manner, and they relies on some hard mathematical problems. Digital signatures is based on a discrete logarithm problem, and it is computationally infeasible to break these algorithms using classical computer. And also hash functions relies on pre-image and collision resistance, and if you apply some attack using brute force, you will see that it is really infeasible to break them. And actually, the main idea is this. You can compute easy one way, and the other way it is computationally impossible to find private, for example, private key. If you see the public key, you cannot compute the private key. And also, if you see the output of the hash function, it is computationally infeasible to find the input of that hash function. Okay, everything is nice, but quantum computer plays a different role in this game. So, okay, I will try to explain in a simple way. The first thing is this: quantum computer is not a faster classical computer. It's not a faster CPU or GPU. It totally works in a different space. You know that for classical computer, we have bits. And for one bit, it can be 0 or 1, either one. But in classical quantum computer, we have qubits. And for that qubits, it can be 0 and 1 at the same time. Okay, yeah, it's a bit different meaning, but we call this one a superposition. And using that superposition, you can compute different possibilities at the same time. And we have also different properties for that quantum physics. Now you can design a different type of computers using that quantum stuff. Cool. And also the other myth is quantum computer do everything faster. It is totally wrong. For everyday using, we still have to use classical computer. For example, you don't need to use quantum computer to send Instagram post. Okay, yes, it can be cool to send Instagram post using quantum computer. Hey guys, I am sending this post using quantum computer, but it is totally inefficient. You don't need quantum computer for this one. But for some other problems, more important problems, you can use that quantum computers, such that breaking some cryptographic algorithms, breaking some mathematical problems, or for some optimizing problems. Therefore, we have to know that quantum computers do not everything faster. Okay, so for cryptographic perspective, we have two different algorithms, and these algorithms works on quantum computer. They cannot work in classical computer, and you can use that algorithms to break some cryptographic algorithms. And the first one is Shor algorithms, and it's published 1994. It is a really old algorithm. And using that one, you can break all the classical digital signature algorithms, which based on RSA and elliptic curve cryptography. And as I said before, it is really infeasible using using classical computer, but you can easily break these digital signatures using quantum computers. But not all quantum computers, I will explain, because there must be a high-scale quantum computer, and I will explain what it means for this technology. The other parts, which affects the hash functions and symmetric cryptography, we can say that, okay, we are still safe in a safe position. This is not a big problem. Even if there will be a high-scale quantum computer for hashes, we are still in a safe place. It only decreases the security level, half of them. For example, if you want to find a pre-image of that hash function, in classical manner, you have to use 2 to the power of 256 brute force attack. But for quantum, still we have 2 to the power of 128 brute force. So we are still safe in that place. Okay, if you look at the overall picture, that functions used in blockchain space is CDSA, EDDSA, BLS, KZG commitments. They all will be broken using quantum computers. But for the hash parts and Merkle trees and proof of work parts, okay, we can say that we are still in safe position for that algorithms. So what can attacker do if they use high-scale quantum computers? Actually, the result is really harmful. They can empty all wallets which they see the public keys of that wallets, and they can grab a payment while the sending process is still in processing for payment process. And also, they can fake the network messages which the validators try to agree on. And I think the most important part is, you know, there are some lost coins, like Satoshi wallet and the other wallets. And if there will be a high-scale quantum computers, they can take this money from that wallets. Okay, and also this is not just for money, but in this case, the trust of that chain will be changed. You know, the trust of the all blockchain space will be changed if attacker can do this one. And okay, that attacks which I mentioned before is must be available at that time. I mean, if there will be a high-scale quantum computer, then that attacks is really feasible. But also for the past information, can attacker do anything? Yes, there are also some retroactive attacks, which we called harvest now, decrypt later attacks. And I think the only important thing is, for example, we have some privacy coins, and they rely on elliptic curve cryptography. And if the attacker can now take the data and take that all transaction, and if there will be a high-scale quantum computer, then these transactions are not private, cannot be private. It's totally public, and it's also a problem for like Zcash and the other privacy coins. But for the integrity and authenticity part, okay, still there are some times to do that transition before we can see the high-scale quantum computer. Okay, is there any fix for this one? Yes. Actually, thanks God and thanks math, we have some new cryptographic algorithms which relies on different mathematical problems. And actually, NIST started a standardized process for these algorithms, and now we have some key exchange and digital signature algorithms which relies on lattices and hash base and code base and different mathematical problems. Okay, but you know, every time we have a trade-off in this life, and it is nothing is for free. For that new algorithms, the key size and signature size are really big. So for the space, it means a lot of codes for gas cost and other stuff. Therefore, the transition is not easy for that algorithms. If you look at this one, you know, the key size is 10x and 500x, and it is really a big problem for the chain. And okay, but why is recently it's so popular? Because Google, researchers from Google and Ethereum and Stanford University published a paper, and they say that, okay, we improve some things regarding to break elliptic curves, and we assume the high-scale quantum computer will be designed early, which we think before. And what is the expectation for this one? Okay, one more thing. Okay, the capacity of the quantum computers are related to the number of qubits which they have. But there are two types of qubits. One is physical qubits, and the other one is logical qubits. And quantum computer work on in a probabilistic way. Even if you have more physical qubits, you know, there are some error correction problem in that physical qubits. Therefore, this means that still you have less logical qubits, and the important part is for the quantum computer, the important part is how many logical qubits that quantum computer will have. So what is the expectation for that high-scale quantum computers? We call them cryptographically relevant quantum computers. Actually, 2030 is the deadline for that transition. And therefore, the time is really near. Therefore, every project try to do that transition early. Okay, I have to be faster because my time is going. So if you look at the Bitcoin and Ethereum part, they are really aware of this problem, and they started to do some improvement regarding post-quantum technology. And Bitcoin published some quantum resistance address type, and they try to also do some testnet for digital signature algorithms, post-quantum digital signature algorithms. Also, Ethereum published a main roadmap regarding that post-quantum transition, and they will try to fix 4 types of their cryptographic object. Okay, I also passed them. And if you look at the internet, not just blockchain space, but the internet, we can see that most of the other companies do that transition using new post-quantum algorithms. For example, more than half of the TLS is post-quantum secure now. They use that post-quantum algorithms. Okay, for TÜBİTAK BİLGEM, actually, we are aware of this problem. We have done this before because from 2016 we have in active research in PQC space, and you know we have also some responsibilities for national security development. Therefore, we started to work on these algorithms, and we actually do that transition for the other parts. Now we will focus on the blockchain space, and we will try to do this transition from custody space and HSM space, and we are ready for this transition. Okay, actually, you know, at the beginning of the blockchain, there are some hashes and signatures, and the world didn't know these details, and the world needs cryptographers. We help them, and after that, they learn that details. After that, there's a new technologies, zero knowledge, MPC, and the other stuff. Again, world said we need cryptographers. We solve that problems, and now we need. World said that we need post-quantum algorithms. Okay, we need cryptographers, and we try to solve also these problems. And how we will know that the day is finally built? You know the Satoshi wallet. You know the public address of that Satoshi wallet. If there is some transaction in that wallet, you can understand that. Okay, now there is a high-scale quantum computer, and we are really in a problem in these days. Therefore, we have to migrate early, then we can sleep well, and thank you for your time. This is the end of my talk. Okay, thank you.